Here Okay, welcome back, students. All right, let's give a few minutes for people to get in here. Because I've got the calendar up, and the calendar just shows you where we got to be at any given time. Because believe it or not, I don't make these dates up. Like the midterm and the final, those are given specific times. So naturally, the flow of material has got to guide us toward being ready for that time. So if it seems like we're moving fast, it's probably because, in a way, we are. I try to use the O2O time to go over material that is, I guess you would say, supplemental to what we're doing. That's why they call it co-requisite in a sense, because it's the stuff that will help you deal with what we're going over in the credit bearing course. And you'll notice too that I'm putting making these blue because those are linked to YouTube. So, for example, while I was here waiting for this class to start, I downloaded the video for the first section, for the first class, and I put it right here. So when I get the other one tonight, I'll put it right here. And we may go through most of this tonight and then just have 2 days of review next week for the midterm. Because you notice that 1 week I've got slated as midterm. And so the next class will be just finishing anything that I haven't finished tonight. But I'm going to try to do it. And then that way it'll give us a little bit, the formal coverage of it. And then you have the video if you need them. All right. So just notice that that's the tipping point right there. That's the smack dab middle of the semester. Now, I have to say, this semester is going by fairly smoothly and quickly. It's like we're less than 2 weeks away from midterm, and which is the halfway point. And as I had said in the earlier class, we'll go over 10.1, 10.2, and 10.3, and that will be on the midterm with chapters 2, 3, and then the first little sections of chapter 10. And that's got to be on responders, remember. And we doing, strict departmental rules with you can only use the calculator in ALEKS or the TI, and you got to use responders, of course, and no outside notes. And see, after we come back, then we can finish up chapter 10, and then this stuff right here is less of it to do. So then, hopefully, it'll be like taking several bites. There's that old saying about how do you eat an elephant? Well, you just do it one bite at a time. We got to take one chunk. And so if we this big thing, this part first, then it leaves this not being so um, insurmountable. Now, I'll just warn you here, and this is just something to kind of get ready for and make sure you stay on top of it. Usually, chapter 10 is one of the harder sections. All right. So, and that's why I'm trying to follow the logic that I'm doing. Okay, so let's go back to the notes, and I'm just gonna gotta go through this a little how we usually do it. Like I said, it might kind of seem a little bit fast, but uh, I know some of you are not in the co-requisite, but you can get the lecture here if you want it. If you want to see how I kind of tried to fill in the blanks there, and then as I said, is I'll put the lecture, the lecture for this when we finish today, and it may well be all of it. As I said, it's really not as much as it would seem. All right, so let's go over there, and chapter 10 is about probability. Now, probability is a way to quantify, meaning write as a number, how likely an event is to occur. Okay. So we're going to write out numerically how likely something is to happen. So let's just get a couple of definitions first. An experiment, and you can kind of think of this like in as a lab, is just a controlled operation that's going to give us a set of results. Now, the nature of probability is we know what things can happen. We don't know exactly which one. In other words, we can't predict the tossing of a coin, the rolling of a die, the two dice. Okay. So what we do know for example, is this thing called a sample space. If we have an experiment, then the sample space would be the possible outcomes. So for a coin, obviously a coin has got two sides, and we can't show both sides at the same time unless we break it into two pieces. But it has two sides, but it's one coin, either head or tail, and there's exactly two sides. We can look at the sample space kind of as a set, and I'm calling it C for coin, is the sample space for a flip flop. I'm sorry, a coin flip. All right. In other words, there's two possible outcomes. Now, let's just say we want to find out um, how many outcomes there are in the event of a tail. Well, there's only one tail, and you're going to have some questions on there that are going to be rather silly to answer almost, because if they give you something like this and then ask you what the outcomes are or to list the sample space, then you basically just list it verbatim as it's given. All right. So kind of remember these for this little thing we're going to do here. Now let's say we want to find the probability of flipping a tail, the probability of a tail. In other words, we're going to take that coin and flip it. And I got this little thing that kind of does it for us. Let's say we just want to flip one coin. See, we don't know what's going to happen, but we'll know it's a head or a tail. Each time we flip it, we know it's going to be a head or a tail, but we don't know what. Now, some people might think, oh, I can accurately predict. Well, let me try that. Let's say I'm say it's going to be a tail next. What happened? Should be just one there. There we go. See, I got it was a tail. But let's see if I can predict the next one. Would it be a head? Nope, it's a tail. And I would just challenge anybody to try this on their own and see how many times that you can predict the outcome of that coin flip. Well, I can judge what that's going to be, because if you do it many, many times, the more times that you do it, you will get it right about half the time. That's the nature of probability. We know what will happen over time. Okay. So let's go back over to here. So the probability of rolling flipping a tail would be just in the denominator at the bottom of the fraction. It's going to be the number of elements in this set right here, which is 2. So that little 2 right there in that fraction is the denominator. The number of tails is the numerator, which is the top, and there's 1 tail. So the probability of a tail is 1 over 2. And the way we kind of know how to put it as a decimal is, whoops, what did I do? It's 1 divided by 2, not 5. So 0.5. So that's the decimal equivalent of 1/2. That's the probability. Okay. Now, just remember, sometimes in those ALEKS problems, they'll give you a probability as a percent, or identify as a percent, and then you'll have to convert it to a decimal, and then perhaps write it back as a percent once you've answered the question. So just keep that in mind. And that's why in the O2O, I'd had some exercises doing that to get some practice at it, because that's the skill you're going to need here soon. Primarily in the second half, but there'll be a little bit of it over here. Now, an event is simply the subset or subcollection of the outcomes. So if we wanted to talk about the event of rolling an odd number on a single die, now remember there's 6 sides on a die, then we can call the event of an odd number as such. That's the set that represents the event of an odd number on one die. There's exactly 3 odd numbers on one single die. All right. So the way we handle this is by a simple formula that's basically just filling in a fraction. All right. So on any kind of probability, and there's something called theoretical probability, which is what that we deal with when we're dealing with the die, or that we're dealing with the coin. We already know how that comes out theoretically. Now, it is possible to do it empirically, in other words, from collected data, and we'll see a problem like that in a bit. But the formula always works like this. All right. For a probability of any event A, the denominator is just all possible outcomes. In other words, your universal set, here called the sample space, all possible outcomes. Now, the numerator, in order for this to be a fraction, as we're going to see, has to be the smaller number up there, and that'll be the number of outcomes, or the subset of the sample space that event that fits into event A, like the odd numbers, whatever the event is. We're just using an A there just so that we can say it theoretically and not specific. All right. So the number or the probability of an odd number on a single die is the 3 over 6, and 3 over 6 can be simplified down to 1/2 and also expressed as a decimal 0.5. Now, the law of large numbers, it's not really necessary to know that for this, and they don't mention it in ALEKS, but basically what it amounts to is just that. For a coin flip, you're not necessarily going to get what you would think. In other words, you're not getting half and half necessarily. You're getting half and half over a long period of time. And I can kind of express this here. Let's say I flip 10 coins. All right. Let's say, let me see those. This is the simulation of 10 coins. And you notice in this case, we've got 1, 2, 3, 4 heads, but we got 1, 2, 3, 4, 5, 6 tails. It's not exactly half and half, and it's not always going to be, because if we were to do it again, then what happens? We got now we got 1, 2, 3, 4 heads, and 1, 2, 3, 4, 5, 6 tails. So it's not got to half yet. But if we keep doing this and keep doing it and keep doing it, over time, we'll get a relative halfway break, half heads and half tails. Because you probably, what's going to happen is somewhere down the line, you're going to have a bunch of 6 heads and 4 tails, or 9 heads and 1 tail, and you'll have all kinds of different scenarios. But as you add them all up over time, it's going to be relatively half and half, and that's what the law of large numbers is basically saying. Uh-oh. Hold on a second. Anyway, I don't know why this does it. It does. I should have. My monitor keeps going out in the middle of things. So get it here back. But anyway, the point is that as you do something over and over, you know the general pattern, but you can never predict any one outcome. Let me give it 1 minute there. If not, I'll go to my laptop. Okay, there we go. It's coming back. All right. So anyway, let's move on here to the next stuff. Now here's the properties, and you can watch that if you want to. It's kind of neat. I showed it to the people in 020. All right. So the probability that an event, here's what we call properties of probability. In other words, these are things that are true about probabilities. The first one is A, the probability of an event that cannot occur would be zero. And I'm sure everybody's heard someone say that. Well, you got zero chance of that happening. Well, that's what we're talking about. Something that cannot happen or will not happen has a probability of zero. And that's the lowest that a probability can ever be. Because to be lower than that, it would have to be negative. There are no negative probabilities. Now, the probability that an event will occur is 1. In other words, a sure thing would be 1. And that's the maximum that it can be, is 1. So that means every probability is a number between 0 and 1. And I say inclusive, meaning that it includes 0 and 1, the two ends, the not happening and the will happen. And this is just kind of a little breakdown of how it comes about. All right. On the left-hand side, the impossible is 0. And as you go to the left, from the left to the right, you're increasing the probability. So as you go along here, it's still kind of unlikely when you get here. And then you get up here, and this is what we'd call a 50-50 chance. In other words, like the coin flip. And then as you get here, you're getting into higher values, and those are more likely. And until we get to 1 is when we're certain. And that's the end. Now, this last property just states that the sum of all possible outcomes of any given experiment is 1. And in other words, what that means is if we take all the individual probabilities, like for example, remember the 1/2? So he said the probability probability of a tail is equal to 1/2. So the probability of both 1/2 plus 1/2 is equal to 1. So that's what this one right here is saying. It's simply saying that the sum of all probabilities of a given experiment will add up to 1. And you can kind of see it too, because if you got 6 sides on that die, there's only 1/6 for the number 2. There's only 1 2 on there. There's 1 out of 6. There's 1 3, 1 4, 1 5, and 1 6. Each one of those is the same probability, and that's what we call equally likely outcomes. And if we add all those up, we got 6/1/6, which is 6 over 6, because it's got the same denominator of 6. And then we just add all the numerators. 6 ones is 6. 6 over 6 is equal to 1. And then that brings us to this thing called the complement rule. The complement rule is written like this. I think that wish I could see an Alex right now. I think it might be written like this. Let me see if I can do that so it looks like Alex. But this is the same complement rule from chapter 2. So in the ALEKS problems, they'll give you this, and they'll say, what is this equal to? And so you pick, if it says 1 minus the probability of not A, then you would pick probability of A. But if they give you this one, the 1 minus the probability of A, then you would select probability of not A. That's all they're asking you. They're asking you to finish that formula right there. And there's two different manifestations of it. This one and that one. And that's what we call the complement rule. All right, questions? Questions? Whew. Now, here's some data. It's empirical, and it is probability is probability. It's all calculated the same way. The large number in the denominator, the total number of your sample space, and then the numerator is the number of elements in your event. So whether it's from theoretical, like we were looking at with the die and the coin, or like this from something that's observed, then we still calculate probability the same way. All right. So here's a table. All right. This table shows the results of a blood drive. And you can see down here at the bottom that there's a 500. Because all these four numbers, they add up to 500. And I know probably a lot of you folks work in hospitals. And so you're probably familiar with this kind of thing. They don't worry about the positive and negative here. And I know there's even other ways to classify even further now. But we're trying to keep it simple here. That we've got the classes of blood divided into A, B, AB, and O. And so out of those 500 people, we had 223 that were type A. We have 51 that were type B. We have 16 that are AB. And we have 210 that are type O. And again, you can see they all add up to 500. All right. And that's as it should be. Because the 500 is our total sample space, like our universal set. It's all of them put together, all four of those. Now, given that, we want to find the probability first of AB. And I've already done it here, but I want to try to do it kind of where it looks more like a real fraction, where we got a top and a bottom rather than like side to side. And this is one reason why I don't like the TI calculator so much, because when you write things out, it looks like this, that slanted type way. You don't have it appear how you would normally write it out or see it in a textbook. So I'm going to try to do that. And the good thing about the ALEKS calculator is they have a nice little fraction tool in there for you to be able to put in numerator and denominator, and it makes the calculations a lot nicer. All right, so let's try to do that here. So let's find the probability of AB. So what this is going to be is put a little fraction bar there. So the number of AB, number total. All right. Okay. So that's going to be equal to. So how many total do we have? How many total?
500.
500. Thank you. Yeah. All right. So that's a denominator. Big number always goes at the bottom when you're dealing with probability. Never have a larger number in the numerator. The larger number will always be in the top. So how many now are there that are AB? 16, right?
Yes.
Okay. Now we could go with some simplification on that. If you divide both numerator and denominator by 4, we're going to have 4 over 125. And that would be called the simplified fraction. And you're going to find out that in ALEKS, especially after midterm, they expect you to simplify your fractions if they ask for the answer in a fraction. So it would be very tempting to put that in. But this is what they're going to grade you on, whether you have this in there. And I think it's some, maybe for a little while they'll warn you, and then you get later on, they don't warn you, they just mark it wrong. Now, the good thing about this is that TI calculator, and y'all can remind me about this to kind of, let's see. But this calculator will do fractions, and I'll find a video to share with you by next week, because that's before you need it. But I don't think you'll need it before midterm, actually. But anyway, there's a this one has a the good thing about this one is compared to ALEKS. The ALEKS calculator does a really good job at everything else, but this one will simplify the fractions for you. And I kind of, oh, that's 10-pack. I said, what in the world? $152. That still seems like that's expensive for 15. And for a while there was 12. But anyway, this one, and I'll just kind of try to show you, is the button here. It's the blue button, so you got to hit second, and then you hit this thing. It says ABC, and that's the one that simplifies fractions for you. But anyway, and I wouldn't show you that unless you figure it out. But I actually, when I was in school, I mean, I couldn't have got by without that. I had a calculator that would do that. All right. All right. So let's do the next one, O. All right. So the probability of O all right, let's see. So down here, again, we're going to have that 500. And what's going to change now, until we get another experiment with different values in it, another table, we're going to be using the 500 for all of these, except for the next one, but that's a special case. We can use it, but I'm going to show you a shorter way for that one using the complement rule. Anyway, now for O, two, one, zero. So I'll just kind of tell you a little secret here about simplifying fractions. If they both happen to end in a zero, the numerator and the denominator, that's essentially the same thing by crossing those out as dividing both sides by numerator and denominator by 10. And that's your simplified fraction there in this case. 21 over 50. And as you can see again, 21 divided by 50. It's decimal wise 0.42. Okay. So you got to watch out. Sometimes Alex will ask you for sometimes, like I said, they'll ask you for decimal. Sometimes they'll ask you for simplified fraction. And then sometimes, not in this case, because it's there's no values past the 2, they may ask you to round it off. So that's again why I had that's why I had that little the little thing that I had in the that the valuation too, because those skills we've been trying to work on them. They're in the 020 and then the path over there, but those are the ones we're carrying forward over here that are important. Those rounding things. All right. Now, the last one is this probability of not AB. Not AB. Not AB. All right. Now, there's two ways that we could go about it. The long way and the short way. I'm going to show you the short way, but I'll tell you what the long way is. But one way we could do it is we can go ahead and find the ones that are not AB. Now, this is the AB one right there. And we, as a matter of fact, we already calculated that probability here. All right. So we know that. So what we can do is use the complement rule. Okay. So the probability of not A is 1 minus the probability of AB by the complement rule here. So that would be 1 minus 0.032, which is equal to 1 minus, well, this is the way it would be as a fraction. You could do it either way. If you had it over here, in this case, like we already had it as a decimal, that makes the subtraction easier. Otherwise, you know, because people get freaked out by fractions. But 1 minus 0.32, as I'll show you. So that would be 0.968, about 96, well, actually 97%. So let me just show you how we could do it real quick. If we just didn't use the complement rule, you'd have to add all these other numbers up. In other words, you'd have to add this, this, and this. So that would be do 3 plus 51 plus 210. So 484. So the probably we're going to do it a different way here. Like I said, we'll do it the direct way just to show you. The ones that are not AB are what was it? It was 484, right? Where was that calculator at? There we go. 484. Over the 500. And then let's do that on the calculator, just so we don't need to worry about the fraction because I'm just doing this as an aside. Divided by 500 is 0.968. Same results. It's just that the complement rule will be easier in this case. And that's why we got it. Okay. So that's really the basics of probability. The ones that you'll have in ALEKS, they'll be like most of them would be like a little chart or some kind of a picture so you can see the sample space, and then you can also define the event, and they'll have you create some probabilities. They usually like a little chart, and you do check boxes, and then you calculate the probability of each. All right, now the next thing, 10.2 and 10.3 are these things called counting methods. And what this amounts to is we can't always see the whole sample space. Like in the case of that die or that coin, it's easy to see and keep track of the fact that there's two different sides to that coin and what they are. And then for the die, there's 6 on there. And then we can identify how many even or odd numbers or whatever we want. it's very easy to see when we've got a small sample space. But sometimes if the sample space is large, we don't need to know so much what they are. We just need to know how many there are. So these things called the counting principle. Well, this thing called the counting principle is important because what the counting principle essentially does is it allows us to take two separate experiments, and if we combine them, and let's say, how come that didn't come down? Something weird's going on here. So the way the counting principle works is if you got one experiment that's got M ways to do it, and that just could be anything. And then if you have a second experiment that's got N ways to do it, then if you combine those two as into one experiment, then we find out the number of ways that we can have outcomes by multiplying the M times N. And I'll show you what I mean here by the counting principle. Let's say we've got a opportunity to buy a couch from someplace, Rooms to Go or whatever. Well, let's say that this couch comes with two different upholsteries, either leather or micro suede. All right. And then we can get it in one of four colors. The leather comes in tan, white, red, and green. And then the micro suede comes in tan, white, red, and green. So how many distinct couches would be available? Well, we can kind of see them here, but the math of it is just 2 for the two upholsteries and times the 4, which is the tan, white, red, and green, and that gives us 8 distinct ways. So see, you got 1, 2, 3, and this would be your leather, tan leather, white leather, red leather, green leather, tan micro suede, tan white, red micro suede. I'm sorry, it was white micro suede, red micro suede, and green micro suede. So anytime you combine two different experiments and you want to know how many different outcomes there will be, is you just multiply. All right. But it doesn't have to be just 2 items. It could be 3, 4, or more. Now, let's say that now we also have the salesman come back and say, hey, you know what? We also have these with or without a recliner. So that gives us a third choice. And so each one of those 8 choices up there now have 2 more choices coming off of them. And so now we've got 1, 2, 3, 4, dot, 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 all the way across. So there's 16 different ways to get that couch, because now we take that 8 and multiply it by the 2 for the yes or no on the recliner. And so we have 16 distinct couches now. All right. So let's carry this over to the idea of a license plate. You might not have thought that this is what it's based upon, but yeah, it's based upon the counting principle. Because we can know by what's on this license plate how many possible distinct license plates they are. Because there shouldn't be any two that are alike, because each one of them represents a different vehicle. And sometimes over time, you may have to even change tags. If and it's not just the vehicle, it's the vehicle registered to the owner. So like if you take your car and sell it to somebody, they're going to get a new tag for it. All right, now this license plate scheme has how many different characters on it? I'm going to kind of underline. 1, 2, 3, 4, 5, and 6. All right, there's 6 different slots there, right?
Yes.
Now, let's go back over here to this slot 1, and down below here, I'm going to put how many possible values. And we're not thinking about just this license plate. We're thinking about any license plate. How many possible values could go in this place where that S is at? How many possible letters? In other words, how many letters in the alphabet?
26.
Yeah, it's going to be 26. Okay. So now, how about for this slot, which is also a letter?
26.
26. Thank you. And then how much for that third number slot?
26.
Great. Thank you, Tiandra. That's good. Now let's go over here. And again, we're imagining this is just one possible license plate, but each one of those 3 number slots has a certain number of possibilities now. Okay. This is one possibility. So how many possible numbers could go there? And it's just a single digit. So don't answer
9.
until you're sure. See, that's what I thought somebody would say, because this is what's funny. Watch. Let me show you something.
7.
Okay. No. Watch. I'm going to write out all the single digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. And what's that middle one right here?
0.
So it can be a 0. So that kind of is a little bit tricky. But how many is that? Well, it's 9 plus one more.
10.
That's kind of your 10, all right? It's just that you're not putting the full 10 up there. The 0 is the number that replaces the 10. So now down here, each one of these will be 10. Each one of these has got 10 possibles. All right, and now what I'm going to do is I'm going to make some multiplication signs here. Crude multiplication signs. Just to show you what we're doing. Usually you don't see this in a college class, but like I said, it is. Otherwise I can just put a dot there, but it just kind of, then people will be asking what it means. But this is what we're doing. We're multiplying all these. Well, let's see what happens if we multiply those. All right. So 26 times 26 times 26 times 10 times 10 times 10. And how many possible license plates are there? Well, here it is. And I'm sure that there's some that are kind of saved for official vehicles and such. But the general principle is there's 17,576,000 possible license plates. Now, I always forget about the number of people in Louisiana, but I don't think it's much more than 5 million. So this is certainly enough to give everybody a different license plate. And even for when you take the license plate and you turn it in and somebody else gets it, 5 million will go into that 17 million almost four times. All right. But here's the thing is, take a big state like California. California has got like 30 million more people than 17 million. In other words, they got approaching 40 million people in that state. So there's a potential for 40 million automobiles registered to people.
Mr. Cruz, how you come up with the 10?
So let's
Hello?
go down
How did you come
and
up
just
with
look
10?
at.
Mr. Cruz,
Mm-hmm.
how did you come up with
Felicia, I can see you talking, but I can't hear you. I thought maybe you didn't know your mic was on. You're talking to somebody else. You put your question?
How did you come up with the 10 on the license plate?
See, it's like you're
601.
okay. Talk again.
How did you come up with the 10? How many items did you come up on the license plate?
See, the thing is, you're going in and out. You said 6. Which 6?
On the license plate. How were you able to come up with 10
What are you, like on a
items?
phone or something?
No, on my desk on my laptop.
Oh, okay. Because like I said, is you're going in and out. I can't hear what you're saying. Type it in the chat
All right.
or say it again. See, you come through loud and clear, but you're just doing it for like a couple of seconds.
I say, how did you come out with 10 outcomes
10
on the
outcomes
license
for
plate?
what?
On the license plate.
Because there's 10 numbers that could go to here. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. See that? There could be 10 different numbers right there. There's 10 numbers, right? 10 digits. That's what that
Okay.
is. Like I said, is you just instead of a 10, an actual 1 0, you would have 0, and that's your 10th number.
All right.
All right. Oh, I know what happened. That thing got put into a header. That's why I did that. All right. So California has got like 40 million people. All right. What do you notice that's different than this besides that the letters are not in front, they're in the middle. What do you notice about this? What's different about this from the
You have
Louisiana?
three.
What was that?
You have the 3 listed twice.
No, I'm just saying, well, yeah, but
It
about
has
the
7 numbers.
7 characters,
I mean, yeah, not
okay,
numbers. Sorry.
7 characters, 3 letters now, same number of letters as the Louisiana license plate, but it's got one more number that appears at the front. And I don't know what that, is for, but watch what happens. That that first number there, that's an extra 10. So going back, let's see, let's see, 26 times, whoops. So that's 17,576,000. Now, that's the Louisiana license plate. So let's multiply that by one more number now, because we got an extra number now. So by another 10. So look at that, 175,760,000. So now 40 million can go into that. Like I said, that's more or less the population of California. And what would that be? Like 4 or 5 times, which is what the same proportion is for the Louisiana license plate. All right, so we still got about 15 minutes, 10 to 15 minutes. Let's talk about these things called permutations now. It's not anything different. It's just that particularly a permutation is an ordered arrangement of objects where we have order is important. Very much like what we have here with these license plate, or a password. The order in which you put them in are important. But a permutation, and one type of it is there's this thing called a factorial. And if you look on the calculator, what happened to my calculator? Okay, there we go. And most calculators do it like this. Now on your Alex, it'll look just like this. See, it's got an N, and then it's got the exclamation mark. That's called the factorial key. And that little exclamation sign, what it means is when you put a number there, and when they use N, that just means it can be any number. Really, going back to chapter 2, that's what N is. It's the count. So whatever that number is, then what the factorial does is it starts with that number, subtracts ones and multiply, subtract 1 and multiply, and keeps doing that until they get all the way down to 1. So for example, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5,040. So let me show you on here. 7 factorial then is 5,040. Any other number you want to put it in there, like 4 factorial is 24. 5 factorial. And they get big real quick. See, if you put like 11 in there, see how big they get quick. And this is why the counting rules are so powerful, because they can help us find large numbers that we wouldn't be able to see, because you can't see 40 or 39 million license plate permutations. But in order to calculate probabilities, we can do it with this, because we just need to know how many. It's the count that matters. That's why we had that N over there in chapter 2, the count of what's in a data set. And that's what we're looking at with N in these counting methods. All right, so the number of permutations, well, let me kind of back up. Let me just kind of explain to you. Let's say we've got a big bag, and it's got a bunch of miniature pool balls in there. And I can't remember, I used to play pool, but I can't for the life of me figure out how many is in there. I think it's 15 pool balls, 1 through 15. And then 7 of them are solid, 7 of them are striped. And then you got 1 through 8, and then the black one is in the middle of the 8. All right. So let's say we got a bunch of those, except small ones that we could grab, and you got them in a bag, and you're going to reach your hand in there and pull a handful of them out. Now they're of such a size that you're can only pick a certain amount of them out. So your handful is always going to be smaller than what's in the bag. So you're going to go in there and you're going to pull them out a handful. And whatever that handful is what we call R. And the N is the number in the bag. So what we got here on this is the P stands for permutation, and that means just ordered pullouts. In other words, we read it as the number of permutations when selecting the handful or object from in the total bag, where order is important, is given in this formula. And so you fill in this with the large number, this with a small number, and this is your formula. Let's see if we can do one before we end up here. All right, so we got somebody with a cell phone here, Shanna, and it's got 17 contacts. She's got 17 contacts on her cell phone, and she must have a whole lot to do because she wants to put 4 people on speed dial. And so she wants to find out how many different ways she can do it. All right. So how can we do that? Well, we're going to fill in this little formula here. N is equal to why don't you make me a little n? Let's leave it like that. N is 17. There we go. Trick it. R is equal to 4. And where's the 4 coming from? There's your 4. So this is our N, and this is our R. Sometimes they'll be written. Sometimes they'll be written out as numbers. Sometimes they're in letters. So you got to watch that. But usually that's all you need. So now we're going to take this and we're going to find P, and the 17 goes over here. The big number is always on the left. So this is going to be equal to, let's put ourselves a nice little fraction bar. And then up here, we're going to put 17. And then we're going to use that new symbol, the factorial sign. And we'll see what to do with that in a minute. And then down here, it's going to be 17. I'm going to put it in parentheses because it's in parentheses up there. We can simplify in a minute. Okay. So what's 17 minus 4? Anybody got any?
13.
Sure is.
$17, $16, $15, $14. It's gonna be
So that's still up there. And down here is going to be that 13 that we just mentioned. Okay. Now, what can we do with that? Well, it's a little bit complicated. We can use the Alex calculator, and I'll show you how to do that next week when we're working with a view and with a review, because I can pull it down then real easy. But basically, it works like this. And I'm going to have to go quick because we only got 5 minutes. The hard part about the virtual thing is writing it out. I can do this on the board with a marker in just a few minutes. But on here, it takes a little bit longer because you see, I don't draw so well quick. All right, so up here, I'll make this real long just to kind of show you what that means. All right, so up here, 17 factorial means 17 times 16 times 15 times 14 times 13. And then it's dot, 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 down to 1. Okay. Now, at the bottom, we got something similarly, except it's
13 through 1.
13 times 12. Oops. Times 12 times 11
Times 10.
times dot, dot, dot. All right. Now, the way their fraction works is if these are all being multiplied, in other words, these are all factors. So we can cross anything out from top to bottom like we did over when we were simplifying fractions over there. So what's going to happen here is all of these down here and all of these down here, for lack of a better word, take each other out. Because that up in the top is 13 times 12 times 11 times 10 times 9, so forth, all the way down to 1, just like this is. We just don't have them written all out because it's a pain in the neck. So what we can do to do it, I'll do this real quick. When we do this, like I said, I'll show you how to do it on the calculator.
No, unit.
And Alex, which is really neat to use. So I can rewrite this like this. Instead of going all the way out. So instead of writing that all the way out, I'm just going to put my exclamation part there to show that it goes on. And then down here, it's just basically 13 factorial. All right. So what happens? Well, the same thing. This one and this one take each other out because anything divided by itself, even if it's 13 factorial, will be 1. And so what's left is simply (17) times 16 times 15 times 14, which is equal to what? (17 times 16 times 15 times 14). So this would be 57,120. 57,120. So there's a 57,120 different ways for Shauna to put 4 speed dial people out of her 17 contacts. All right, so we hit it up right on the money. So have a good weekend, but try to keep up. If you can get through all the chapter.
Have a great
10,
one, Mr. Cruz.
great. Okay, bye-bye.